we will use the method of undetermined coefficients to determine the form of a particular solution. Notice here we only determine the form and not the actual particular solution. Right. Remember, this is just like kind of guessing the type of the solution. For example, if we have the form of that particular solution, then our guess will be in the form of at squared plus bt plus c. And here we do similar thing. However, just like when we did earlier, when we use the undetermined coefficient, we always have to find the solution to see if there is any redundancy with the particular solution here and here. Right. So we kind of have to find the solution first. However, we don't have to fully find the whole general solution. All we need to do is find the eigenvalues, because from the eigenvalues we can determine if it is in the form of the input function on the right. We can tell right away. Right. So let's just find the eigenvalues here. Which is determinant of a minus lambda I equal to 0. So we have determinant of the matrix A when we subtract lambda on the diagonal. Determinant of that equal to 0. This is again a scalar equation. So find determinant minus 0 times 6. So that's all we have. So from here we can say lambda equal to 6 and lambda 2 equal to -1. Right. If we have that, then the solution will be resembling the form of C1 e to the 6t some vector v1, and then C2 e to negative t some vector v2. V1 and v2 are eigenvectors corresponding to the eigenvalues of 6 and -1. Right. Look at the form here, e to the 6t and e to negative t. That is not in the same form as the polynomial we have for this input function. So that's good. So in this case, we say that we just guess the solution directly from the problem, and the solution, the general solution, the homogeneous solution does not affect our guess. Right. So if we guess for that function, that will be in the form of at squared plus bt plus c, and this of course just actually in the form of just at plus b, second degree polynomial, binomial. Right. Notice that if we have to guess one equation for both of them, this equation will suffice. So we only need that, because in that polynomial also cover the other form. So with that, our guess will be just the equation in the form of t squared. This time we do not use a as a constant, as a scalar. We use a constant vector a plus t constant vector b, and then the constant vector c. So we write that in the vector form as opposed to a polynomial we have earlier, because those two functions represent, we can use just one guess function, just this, to represent both of them. So we just write the guess, the solution, a particular solution will be in this form. we have the similar problem. Here. Again, first we find the eigenvalues to see if there's any redundant with the input function on the right hand side. Right, eigenvalues. Minus lambda on the diagonal, and we just find the determinant. 4 minus lambda, 7 minus lambda, minus -1 become +1 equal to 0. Multiply them out. 28 minus 4 lambda minus 7 lambda minus 11 lambda plus lambda square plus 1 equal to 0. Right. So we have the equation lambda square minus 11 lambda plus 29 equal to 0. Right. What we see is that this solution is something complex, and this should be imaginary. It's the complex solution. All right, which means the solution is in the form of sine and cosine. So the good news is it's not going to be redundant with this input function. So we just guess the solution based on the input function and don't have to worry about the general, the homogeneous solution in this case. Right. Now, when we guess this form, we're going to guess of the form of a plus tb or at plus b. So we have the first degree polynomial times e to the negative t. For the second function, we just have a e to negative t. As we see that for those two functions, if we choose the top function and we let b equal to 0, let t equal to 1, I mean, if we let a equal to 0, pretty much we cover the second part of the equation as well. So if this one we let a equal to 0, then we just have this, which is the form of the other function. So at plus b to e to the negative t will suffice for the solution. So the particular solution will take the form of, again, it's not in the constant scalar a, it's going to be the vector a. Or we can just say it's going to be t e to the negative t a plus e to the negative t b. So just guess the solution in that form, and that's what we have.